Suppose we have a Bellman equation and we want to solve for the unknown value function, which is a function of the vector of state variables denoted by x, and let A denote one or more control variables, which take values in the control space, which is a set of possible actions given the current state. If the control space is large, then the value function is computationally expensive to solve, as it will take longer to find the values of A that maximize the objective function. The dimensionality of the control space increases exponentially as the number of state variables increases, which makes high-dimensional problems computationally infeasible to solve. This is known as the curse of dimensionality. Approximating the value function with hierarchical linear splines with locally adaptive refinement procedures help alleviate this problem. Suppose we have a one-dimensional function f, which is defined on the unit interval and maps the parameter x to some scalar f of x. Let's assume throughout that our function is expensive to compute, and we want to approximate our function with a less expensive function. We'll construct our function approximation by interpolation of f. That is, we'll partition the unit interval into an arbitrary number of grid points, and evaluate our function at each grid point. We then use these values to define our function approximation. There are many ways to do this, but the simplest may be to connect the values with straight lines. Then our function approximation would be given by the green line. This would be an example of linear spline approximation, which means that the function approximation is defined piecewise by linear functions. If we increase the number of grid points, then our function approximation becomes more accurate, at the cost of it being more computationally expensive. Notice how the linear spline approximation is good where the function is approximately linear. However, the approximation is worse where the function has a lot of curvature. What if there was a way to increase the number of grid points only at areas where there's lots of curvature? This gives motivation for hierarchical linear splines with adaptive refinement. But to understand this method, it's easiest to begin by understanding how we constructed the linear spline approximation in more detail. Full grids subdivide the unit interval into intervals of equal size. For simplicity, let's choose a number of intervals to be a power of 2, where L denotes the level of the grid. If we define h to be the inverse of the number of intervals, then this gives us the grid spacing, which is the length of each interval. Then our full grid can be constructed by having a grid point at the boundary of each interval. Then for each grid point, we can define an associated basis function. For a linear spline approximation, the simplest is to define a piecewise linear function, and our function approximation will then be constructed as a linear combination of these basis functions. It's easiest to understand this through a visual representation. At level 0, there are two grid points at the boundary 0 and 1. Each basis function takes the value 1 at its corresponding grid point and 0 at the other grid point. At level 1, we subdivide the unit interval into halves. Therefore, there's an additional grid point at 0.5. Except at the boundary, these basis functions look like hats, where they are 0 everywhere except between the two neighbouring grid points, where it increases linearly from 0 to 1 and decreases back again from 1 to 0. Suppose we want to approximate the function f of x equals to x squared sine pi x using the linear spline approximation. Let's choose an arbitrary level, such as 2, so we have grid points at every quarter. At each grid point, we fit each basis function to the curve. What this means is that the function is evaluated at each grid point to get a coefficient for scaling the basis functions. Finally, the function approximation is given by summing up all the scaled basis functions, which is equivalent to connecting the peaks of each basis function with straight lines. Now let's consider a hierarchical linear spline approximation with full grids. Note that in the previous examples, the set of grid points were nested, which means that the set of grid points at each level contained all of the grid points from the previous level. To define a hierarchical basis, we consider only new grid points that were not already contained in the previous level. This corresponds to grid points with odd indexes. This means that our grid can be decomposed into L+1 incremental grids, and our grid can be represented as a union of these disjoint sets. Again, it's easier to visualize what's happening. The setup at level 0 is the same as before. There are two boundary grid points at 0 and 1. At level 1, there is only one new grid point at 0.5. Now we don't include the boundary values 0 and 1 since they appeared in the set of grid points at level 0. At level 2, there are two new grid points at 1/4 and 3/4. Again, we exclude all grid points that appeared in any set of grid points at any previous level. The hierarchical basis will span the same function space as the nodal basis defined previously. The difference is that our function approximation will be defined recursively, starting from level 0 to a maximum hierarchical level. Suppose we want to approximate the same function as before using the hierarchical linear spline approximation. We choose the hierarchical level to be 4. We start by approximating the function at level 0. At level 0, the boundary values are both 0, so the basis functions are scaled by 0 and they look flat. At level 1, we evaluate the function at the grid point half to get a coefficient to scale the basis function. This gives us our function approximation at level 1. And then we compute a residual function, which is the difference between the original function and our function approximation. We then repeat this process all the way up to our predefined maximum hierarchical level. Here, the orange lines represent the basis functions that we use to approximate our function. Then our function approximation is given by the sum of all these basis functions, given by the green line here. The function approximation is actually identical to the linear spline approximation. However, the difference is that we use a different set of basis functions, and so we have a different set of coefficients that scale the basis functions. The coefficients here are called hierarchical surpluses, which measure the contribution of each basis to the function approximation. This will allow us to use an adaptive strategy, keeping only the grid points where the contributions made by the basis functions are high. The process for the adaptive hierarchical linear spline approximation is the same as before, except for each level, we evaluate whether the absolute value of the hierarchical surplus exceeds some predefined tolerance level epsilon. If the hierarchical surplus, denoted by alpha here, exceeds the tolerance level in absolute value, then the corresponding node becomes a parent node, which means that it will create 2 neighboring nodes in the next level. If the hierarchical surplus is less than the tolerance level in absolute value, then the corresponding node becomes a terminal node, which means that it will not create any neighboring nodes in the next level. This process is repeated until either the maximum hierarchical level is reached or all nodes become terminal nodes. Let's approximate the same function as before using the adaptive hierarchical linear spline approximation. In addition to a maximum hierarchical level, it's useful to set a minimum hierarchical level to prevent the function approximation from terminating too early. Here we set the minimum hierarchical level to be 1, which means that for level 0, all nodes will become parent nodes regardless of the size of the hierarchical surpluses. The process repeats as before, but each time the absolute value of the hierarchical surpluses are evaluated compared to the tolerance level, and if the absolute value of the hierarchical surpluses exceeds the tolerance level, then the node becomes a parent node, indicated by the green dots. At the lower levels, all the hierarchical surpluses are high in absolute value, so all the nodes become parent nodes and create children, which are the neighboring nodes at the next level. At level 3, some of the hierarchical surpluses become lower than the tolerance level in absolute value, and therefore the nodes become terminal nodes, indicated by the red dots. These nodes don't create any neighboring nodes in the next level. The algorithm stops after reaching the maximum hierarchical level, which we set at 4. Then our function approximation is the same as before. We sum over all the basis functions to create our function approximation, given by the green line here. In this adaptive approach, we use fewer grid points in comparison to full grids, while the function approximation is not that much worse. This method could be generalized to higher dimensions where the benefit is more realized, but I'll leave that as a topic for a potential future video. To conclude with, I'll leave you with the animation for approximating a more complicated function which has more curvature. Here, the benefits from using the adaptive hierarchical linear spline approximation will also be more obvious.